of the famous book on reinforcement learning that you have read. Thank you.
Okay. Well, good morning. Hey, you guys, I need to get to know you guys just a little bit, you know? You guys are from, how many of you guys are from Chennai? And so how many of you are not from Chennai? Maybe it's roughly equal. Good, good. And how many of you are students of computing science? And electrical engineering? And control systems? And psychology? Neuroscience? Okay, economics? Okay, so we have pretty much a computer science crowd. That's good. Okay, now how many of you know, have already studied something about reinforcement learning? Okay, now this is the hard one. Feel free to raise your hand. How many here really don't know anything about reinforcement learning? A few. Okay, so some. Now, this workshop is about advances in reinforcement learning, so it's going to be, not everything will be introductory, but everything is meant to be at least understandable, at least at some level. So even if you don't have background, if there's something I can say to clarify something that might seem muddy, feel free to stop me and ask a question, and I'll try to give you a level at which to understand it. So today, I'm going to give several talks, but today, just the one talk. And so today I thought, particularly since this is leading off the workshop, that I should talk maybe not about the detailed technical results or new stuff, but give a sense of at least what I feel is the ambition of the field and why it's important, why we're here, and why we're here now, and at least what my ambitions are. So, and I think of it as ambitions for both reinforcement learning and artificial intelligence. I guess maybe many of us are engineers or computer scientists, so maybe we're comfortable with that. So why does it matter? Why are we here? Well, let me give you my own personal view of these things. Well, first of all, there's a science of mind which is broad. It covers both the engineering, the computer science, and the natural systems, minds, people, and animals. Of course, in the future, not of course, but my perspective is that in the future, most minds today are people and animals, of course. But in the future, and happening now, gradually more and more we have created or designed minds. And one way to think about reinforcement learning is it's the beginning of a science of this general topic of how minds work. Okay, so I'm talking about minds, and I should tell you a little bit, almost a definition. Well, a mind, I mean mind roughly is something that has intelligence. Okay, it's like mind is the sort of the thing that is intelligent, intelligence being the property. So what is intelligence? Well, I've assembled three quotes. First we have John McCarthy. No, first we have William James, a psychologist. The hallmark of mind is constant ends from variable means. This is just the idea of having purposes or a goal. If you have a system that you find it useful to think about as varying what it does in order to get what it wants, then that would be an intelligent system or a mind. John McCarthy says the same thing, really, is that intelligence is the computational part of the ability to achieve goals. So goals and then computation. These work reasonably well as working definitions of what intelligence is. You might notice that, particularly in this last one, it's not a question of a system is intelligent or not. You should stop ever asking that question, like, our dog is intelligent. Don't ever ask that. Is the computer chess playing program intelligent? Don't ask that as a yes or no question. It's a question of degree. There's a certain extent that the chess playing program is intelligent. In other words, it just means it's useful to think about it in terms of goals. If you're playing the chess playing computer, you might think that it's trying to win. Okay, it's actually a very useful way to think about it. But it's not, intelligent or not intelligent. It just has degrees. A thermostat is slightly intelligent. It has the goal of keeping the room at a good temperature. I might want to do one more. It's not quite a definition. Actually, no. In the eyes of the beholder. So the thermostat, there's no fact about the thermostat or the chess program that it is intelligent or is not intelligent. The fact is in you. It's in you as an observer of the system. You may find it useful to think of it as having a goal. And there'll be a degree to which you find it useful to think about it as having a goal. It's really useful to be able to leave your house and the thermostat will keep track of the temperature. I don't know, at least that's the way it is in Canada. Where I come from, in Canada it's cold. So you leave the house, you need to know that your thermostat will keep the pipes from freezing. And that's a really useful thing. And that's why it's really useful to think that there are things in the world that have goals. Okay, my third definition, I like this. It's not really a definition, but Ray Kurzweil says intelligence is the most powerful phenomenon in the universe. Now, the most interesting thing about that, the whole thing about power in the universe is cool, but first, phenomena. Okay, intelligence is something that you come across in the world. You discover that there are, like animals and people, these things which try to achieve goals. And now we come across systems, designed, created systems that it's useful to think in terms of goals, like the thermostat. So it's a phenomenon that we observe and we find useful to think about the world in terms of goals. Most powerful phenomenon in the universe. That could be argued, but the point is, it is powerful. And if you think about the universe as evolving, life forms on planets, and life begets intelligence. Intelligence is a powerful thing. The intelligent beings pretty much run this planet, and as we try to make more intelligent systems, they will become more and more powerful. So I want to actually talk about that as we develop AI. So this is the grand ambition, of course, to make beings, to create artificial intelligence. So I'm going to talk about the coming of artificial intelligence and ask whether we should take it seriously. But first, again, a few definitions so you know what I'm talking about. So this coming of artificial intelligence is when people finally come to understand the principles of intelligence, what it is and how it works, well enough to design and create beings as intelligent as ourselves. So I think this is just like a really fundamental goal for all of science and engineering, and really even for the humanities. Really, we want to understand ourselves. We want to understand what minds are. This is a big thing, a really big thing. It'll change how we think of ourselves and think of it's more important even us as a species. Will inevitably lead to things that are more powerful. And so I just want to spend a few slides here trying to persuade you that we really should take this seriously and it's not just way out there. But this thing, you can also think of it just as science. This is a big scientific prize, an opportunity to understand how the mind works. This would be a big deal, will be a big deal. You can compare it to like Watson and Crick discovering DNA, or a good one maybe is Charles Darwin discovering evolution. That changed our view of of ourselves in a very fundamental way. You can also compare it to the discovery of atomic power, atomic fusion, and that's nice because it has both good parts and bad parts. And maybe the same is true as we figure out intelligence. maybe a power that is more powerful than us. Could be good, could be bad. We might have to worry about that. But first, let's ask some of the basic things. So, is this possible? Is this possible that we could make superhuman intelligence? Well, I think it's, it's hard to ask these kind of questions because you have to, you're not going to find it in a book. You have to look into yourselves and see what you think, and we have to find different ways of thinking about it. But I'm just standing here, and I think it's definitely possible because I'm thinking people are basically machines. They're biological machines. So if we understand them, we can kind of reverse engineer them. It's difficult. They're extraordinarily complicated machines. But science is persistent. Engineers are persistent. Eventually we'll understand them, how they work, and then surely we ought to be able to do some things better. We'll have new materials that aren't available to biological systems. How could there not be something we can't improve? With design, you can move faster than with evolution. So I think it's entirely possible that we could make, that those such machines might exist and that we could make them. Okay, but if it's possible, that doesn't mean it will happen. So will it happen? And of course it won't happen if we destroy ourselves as a species, if we have nuclear weapons. Maybe there's a 10% chance of that, or maybe better, I don't know. Well, let's assume that that doesn't happen. If that doesn't happen, then, you know the way the world works. There are iPhones and Google. It's inevitable that there'll be economic incentives. Each step will be an economic incentives that we want to make a smarter and smarter system. We will never want to stop. And I think it's also extremely unlikely that we could force this to stop. That some governments could say, okay, no more AI, because there are many governments and many people and many organizations, and there's too many. If the U.S. doesn't do it, then India will do it, and there's so many actors. Russia will do it, or China will do it, or North Korea will do it. You're not going to stop this, okay? Too much value to be had. So, I'm thinking, yeah, it will happen. I haven't talked about when it will happen yet. That's what we'll talk about next. But eventually, if we don't destroy ourselves, it will happen. So before asking when, let's just sort of recap the view here. The view is that this has to do with the development, maybe the development of the universe, but certainly it's a milestone of life on Earth if we can make artificial intelligence. Milestones like, we have the Big Bang and the formation of the Earth, and then we have life. Life is all this green stuff. And then here's when we get to the machines. So what we're talking about is this transition, which has already started. We're already becoming highly technological for 200 years, and we already have computers, primitive nanotech. Let's talk about what words we should use, because words are important. What's the right words to use for this? I said the green stuff was life, but I don't really like calling it life, because as these intelligent systems that we create become better, it feels more appropriate to talk about them as living too. And when we look at these, understand these biological systems better, it feels more appropriate to talk about them as machines. So it's not like life versus machines, because our machines are becoming more lifelike and our life is becoming more machine-like. That's not going to be a good way to talk about it in the long run. So I'm calling it the age of replicators. I think what's special about these biological things is they can reproduce themselves without knowing how they do it, right? We can make intelligence already in the old-fashioned way by making babies. Okay, we could always do that. So these are replicators. They don't know what they're doing. They don't know how they do it, but they can make more of themselves. And the special thing about these is these were designed. These were an idea that was in some thing's head first, before it existed. And so this is the age of design. And, right now, if you come down to the earth, you'll see all those trees and plants and people. Most prominent thing are these self-replicated things. But they're also, buildings and machines. And so I think life is developing from the replicators to the designed things. In the future, more and more minds on the planet will be designed minds, as I said early on. So this is this great transition where what it means to be a person or an intelligent being in this part of the universe is being transformed. And you can think about it in many ways. You can think it will mean the end of biology or the end of people. I don't think that's the right way to think about it. I think it's a transformation of people. We will be merging with the machines. We will be becoming more intelligent ourselves. It could work out in many, many ways, and it depends how we treat it, the attitude we treat towards them. So some people think, and people are starting to worry about that, some people think it could be very bad because the machines would be more powerful than us and we would become slaves to them or something. And that could happen. I think one of the best... So how could that happen? I think the most likely way for it to happen would be that people would fear it, would fear that the machines would take over and therefore try to enslave the machines, keep the machines from becoming powerful. Because if you enslave a very intelligent being, it's a fragile situation. If the slaves are more intellectually powerful than you and you try to control them, well, if they ever do get away, what's the first thing that they're going to do? It would be to push the enslavers from their place and prevent it from happening again. So I think the greatest thing to be worried about, if you want to worry about this, is that we might try to prevent it in a crude way. I think we should think about it more, not that we should make slaves or butlers, but we should think about, the evolution of the universe. And these are going to be our descendants. This is where we're going to end up. Okay. Do have to get back to reinforcement learning. But why am I telling you all this? Because it's so far off in the future, perhaps. So we have to ask this question at least a little bit about when will it happen. And but that's a hard question. No one knows. Don't really want to make a workable prediction. But I do want to say the most important thing, which I think I'm not going to try to answer that. I want to ask: is it going to come in our lifetimes? Is it going to come during our careers? Okay? So, and the big point here is the might. Might it come in our lifetimes? All I have to do is suggest to you or persuade you that it might happen in your lifetime. And it's such a big event, right? It's such a big event, it's such a big scientific prize, that if it might come in our lifetimes, then we should include it in our plans. And yeah, I think in the end, I'm going to conclude that it will definitely come. Well, no, we might destroy ourselves. So the computational megatrend is just a long word for Moore's law, that computation increases exponentially. The megatrend, more generally, is really broader than Moore's law. This thing is held for 60 years, and we can expect it to continue. It's very predictable. These are some standard graphs of computer power in various sense, RAM and memories of various performance, and they're all just increasing exponentially at steady rates. This is a famous graph of this phenomenon where we have time here along the bottom, and we have processing power MIPS per thousands of dollars. So this is computer power per dollar. And the computational megatrend is that this tends to be a straight line or perhaps even upwardly curving, and it's already on a log scale. Okay? And so each point represents a computer at a particular point in time and how powerful it was. Okay, so it's going up and up, and this figure was made by Hans Moravec, an AI researcher at CMU, and he added one more thing, which is sort of a rough, very rough estimation of how much computer power is performed by various biological systems, including people up near the top. And so it's as I say, it's rough, but it's not unprincipled. He was an expert in how the vision systems work and how the retina worked, and he was extrapolating the computer power of the retina to the rest of the brain, basically by mass. So this is uncertain, but remember this is an order of magnitude, so we don't have to know exactly how much computer power a human represents. And we project forward on one of these trend lines. We reach the human level right here at about 2030. Okay? Could be earlier, could be as early as one of these, maybe the mid-20s, 2020s. And of course it's very rough, as I said. And what's to be off? To be off by an order of magnitude. 10 times. It turns out 10 times is how many doublings? It's a little more than 3 doublings, so it's 5 years. So if we need 10 times as much processing than we thought to be a human, we just have to wait another 5 years. If you need 10 times less, it might come 5 years earlier. In that sense, it's a very robust calculation. And people have known this for a long time. This kind of graph, this doesn't even have the latest data points. Right? This ends a little after the 2000s. This has been known about for a long, long, long time. And so here's David Waltz in 1988. He's a recent president of AAAI, basically saying we're nearing this point when we can construct machines that could be as intelligent as us, and the data seems to suggest that could happen for $1,000 at about 2030. But of course, this is just the machines, right? It's not the missing part is the ideas, the software, the algorithms, and we don't yet have those. We don't know when we will have them, and so setting aside the uncertainties, but if the hardware was the only limitation, we would be able to do it by 2030. So will it happen then, or will it not happen then? Will it happen when the hardware is available? This is a question for you. No one knows. But I'm thinking that once you can do it for $1,000, it's going to be a tremendous spur, tremendous desire, tremendous push to develop the algorithms. And maybe the algorithms will be ready when the hardware is available. Maybe. We can see this happening already, the spur, the fact that there are more and more companies like Microsoft and Google that are working on AI. Facebook has major labs to do machine learning. All those companies have major labs. And that wasn't always true. There's a spur. As it becomes cheaper, like if you could make a person and it cost, $1 billion, would anyone do it? Would you make an AI if it cost $1 billion? I think you'd rather just make another person in the old way. It's just not economic. Okay, but if you can get that intellectual power for $1,000, then maybe it would make sense. And of course, soon after, these just get more and more. So in this context, what are we to do for studying reinforcement learning or the AI? To me, these are essentially simultaneous. Or rather, AI is part of reinforcement learning. Reinforcement learning is broader. It includes control theory, psychology. So, but what are we to do if this prize is maybe within reach? Yeah, maybe within reach. I just want to say a little bit more about that. So 2030, 15 years from now, will we have AI? I don't know. Do you guys have any feelings about that? I've just been talking about that. Does it seem plausible?
It's a bit wonky to me what you mean by super intelligent things going to happen. And I feel it's already happening in various dimensions. I pick out my phone. I have something that will tell me how to get from here to somewhere else, right? This is superhuman. There isn't a single human being on this earth who can tell me how to get from any point to any point in most of these world. So in ways that we don't even realize, it's already creeping up on us.
We have some superhuman abilities, but I don't think you would argue that we understand the principles by which the mind works.
So that is what you mean is going to happen in 2030?
Yeah, I think that's what I meant to have said earlier. Understand the principles well enough to make things as good or better. As good. So, is it going to happen in 2030? Did I quite say that? I think I didn't quite say that. I said it could happen then. And I'm going to, so just to make that more specific so you know what I'm thinking. I'm thinking there's like a 25% chance 2030 we'll be able to do it. Okay? And because we don't know how to do it yet, breakthroughs have to happen in the kind of ideas that we're going to talk about here. And breakthroughs can't be manufactured, they can't be planned, they take uncertainties and so forth. So let's say 25% chance. But there's this tremendous economic spurt. If it's not done in 2030, then it'll be 2035 and 2040, and computers will be even more powerful, and the guy who figures out how to harness that into an intelligent, designed AI it'll be extremely valuable. It'll become more valuable for every year that goes by. And there's just going to be a greater and greater push. There will be more and more research labs. There will be government projects to figure out AI before the other country figures it out. Still, you can't, even no matter how much the government wants to do something, doesn't mean if it involves science and research and breakthroughs, it doesn't mean it's going to happen. So I add 10 more years. I would go up to 2040 and say that's the median. 50% chance by 2040. And so I think you're starting to get the idea there's a very broad spectrum of years by which it might occur. It might occur 2030 or 2040 or 20 years after that. Very, very broad. That's why it's pointless to make a prediction, like, pick a year, say it's going to happen that year. You have to describe the distribution. I'm just trying to describe the distribution. But 2040 is a good number because that's, half of it, half the distribution, I'm thinking is done by 2040. And that then is the answer to the original question: is if you believe this argument anyway, that you should take it seriously because many of us hope to be alive 2030 or 2040, and still in our careers, and if all this is happening and you're in the field, this is important for you. You might want to plan for it and work into it. How can we do something relevant to the prize? What strategy should we follow? What issues should we consider? The main one is that the computational megatrend diminishes the importance of special case solutions increases the importance of general methods. So for so much of AI, they've tried to build in special cases. But if you have computation and memory, you can do general methods like search and machine learning. The rise of machine learning has to do with the computational megatrend. Like in the 70s, late and 80s, when I started out, it was all about, oh, we need to make AI, and then we'll worry about how to learn it. And now, AI and machine learning are almost the same thing. So nowadays, the key question is scalability. Will your machine scale with increasing computer power and increasing data? This is the main implications for AI. Now, we have to also make the point, if computers are so big and powerful and fast, do we have to even worry anymore about how expensive our methods are? Do computational costs matter as computers become vastly cheaper? Of course, they'll never be free. But as they become vastly cheaper, can we stop worrying about computation? And if you think about it for a moment, really it's the opposite. Computation's become more important, not less important. And it's because computer power is one of those things for which we have infinite demand. I mean, it's like, energy. If there's a new kind of energy that's, new kind of nuclear power, say, that's really cheap, would we use less energy? No, we would use more energy. Would how we use that energy become more important? Yes, if more and more your system is determined by how you use energy, you then have to become more efficient at it. And if we have some intelligent system that is using immense amounts of computation, then if we can make the computational part work 10 times faster, the system will be 10 times better. So computational concerns will dominate, will become more important. Okay, so I just want to say that this is a long trend. This has been going on for I don't know how long, many decades. And we've seen it happen before. So we should just have some confidence that it's true. So we think about how the whole development of chess programs. In the early days, everyone thought that you should put in human ideas about controlling the center and all kinds of things. But it turned out that the way to win was to do a big search, big, efficient, heuristic search. Computer Go, we thought that human ideas were important, and it's much harder than chess. But recently, we have a breakthrough in Monte Carlo tree search, and now Computer Go is being solved. Again, massive general purpose technique. The massive application of a general purpose technique, Monte Carlo tree search, has ended up winning. In all the natural language processing, it's the same. In the early days, we thought it was to build in human notions and human concepts about language. But statistical methods now dominate. Big data methods dominate. Now deep learning involves very little. All the stuff that the human knowledge they were trying to build in has now been removed, and it's done by general methods. Same thing in vision, object recognition with deep learning, big data sets. These general purpose methods are dominant. So this is the graph for for Computer Go. Remember the game that goes like this? And this is again time, performance in a log scale, sort of a log scale. And this is about this point the field discovered the application of Monte Carlo tree search, and then we started on your standard kind of exponential trajectory. I found this graph kind of interesting. I had my David Silver made this graph for me many years ago when this was the latest point, and he drew the line out to infinity, and I added the last 2 points just by going and looking on the web. What was the performance at the time? And they fell exactly on the line. It really seems to be happening just like this. So I think at least by 2025, with a steady march of computer power, we'll have a world champion in Go. Okay, so the new view that I'm trying to say is that minds are real-time information processors acting with this massive source of data from a complex and arbitrary world. This is not something that we can really leverage our subjective, consciously available human understanding. Instead, we have to find scalable general methods to learn arbitrary stuff about the world. Stop trying to take advantage of our knowledge and just deal with the complexity of the world. So what do I mean by the complexity of the world? So I want to show some quick videos here. So here we have just examples of skilled sensory motor behavior. This is the kind of thing that people are designed for. Interacting with the world rapidly, making choices. You guys like soccer here in India? Yeah? How many of you play soccer? I'm really curious about this. Play soccer? The rest of you are all doing cricket? Yeah. Do you know who this is? That's the comparable Messi. Or there he is, number 10. So look at him. He's aware of, in the corner of an eye, the opponents, where the goal is, where the ball is. Can't look everywhere at once. And he's got to manage all those probabilities. And he makes the goal. So this is very massive. Think of the information processing that he's doing. All those camera images coming into his eyes, all those sense of where his body is, the sort of physics that he's doing to imagine where to move his body and where the ball will go. Enormous computations, enormously rapidly done. And everything is like this. So here, this guy's just trying to swing the bat and hit the ball. It's coming at him so fast that you can hardly see it. He's got to swing long before it gets to him. And, will the swing result in a miss, or will the swing hit the ball way out? Animals, this hyena is trying to escape from the lion. He's trying to predict if he's okay. Maybe he's doing a reinforcement learning. It's sort of like the lion is doing the same thing. Am I going to catch this thing? What am I going to do if I do? Is it going to be one outcome or another? This is a bird flying in real, he's slowed down, of course, but he has to choose all of his muscles to get through the opening and safely. And even, human interactions, we generate real-time actions, and we're trying to guess what's going to happen, and is she going to kiss him? It's all predictions. We'll just move on. So this is the new view, is that it's all about a huge sensory motor problem, and we have to understand it, take advantage of it. We have immense resources to deal with that. But the world is always more complex than our resources. This is the key thing. So it's not good to make theories about the world. You've got to apply your resources, make approximate methods. Computationally frugal methods, because there's never enough. We're finding approximations. I'm not into looking at optimality. It's just a distraction. So we have immense data, which is the sensory motor flow through our bodies and our sensors. But we don't have labels, right? If you're trying to catch the hyena or decide what word to say to the girl or the boy, you don't have labels. But you do have your interaction, and you have to get data from that. So here we are shifting towards generality, approximation, massive computation, learning without labels. This is where reinforcement learning will come in, because we can learn without labels. This is the longest trend in AI. This trend is basically the shift from design to meta-design. The earlier methods have always been use your intuition about how our minds work to make AIs that work similarly. And the modern way, although it's been going on forever, is to instead design in general principles and then let computation do the rest. So yeah, this is my reading of AI, that we've always done the first and then realized that we should have done the latter. And reinforcement learning and temporal difference learning, they are part of this. They are examples of this. They are part of this. So reinforcement learning is learning to control the data, and temporal difference learning is learning to predict the data. They're both these general methods, sometimes called weak methods because they're general. They don't take advantage of domain knowledge. They both proceed without human input or understanding. And they can be done massively, computationally, in a computationally massive way. So this is my summary of the ambition. The ambition of reinforcement learning and AI is we should take the big goal. The big goal is to make strong AIs, to make systems that are as smart as people. And this is part of this longest trend towards general purpose systems enabled by the steady exponential increases in computer power. We're part of this trend, and I want us to think now about where it should lead us in the future. But having said all these things, at this high level, now we'll start to go one level shallower, but I thought I would invite questions at this point. Maybe we could take 5 minutes of questions about how seriously we should take this ambition of making, in our research, of making human-level machines, intelligent machines. Please.
So while I probably would subscribe to your vision, just to be slightly better. There are two ways to think about any system. A physics way of thinking about it and a biology way of thinking about it. Where in physics you say that there is one general principle that is applicable to pretty much every setting. In biology you say that everything is specialized to their job and these systems come together. I mean, merely not come together, but they are specialized in their own subclasses. So you seem to be on the physics side, saying that there is one general principle of intelligence, and that general principle of intelligence is what we're after. And I'm trying to question whether that's really
Not one. I would say there's like 5.
But why? So are humans general purpose? And then when we start thinking about that question, I would say that there is one Messi and there is one the best people, but when we give their examples, but the average is very, very different. And different people have different learning abilities, different people have different observation abilities. Their brains often work very differently. There are studies which show that some people, when they listen to music, they see colors and crazy things happen in the brain. And even from a computational side of things, you have different algorithms which are used for different settings. Minimax for chess and Go UCT, and Minimax does not work for Go and UCT does not work for chess and so on. So do you really believe that there is a very small number, handful number of principles, and why?
Well, yes, I do. And why? I guess why is, I think it's just been the empirical experience in AI. We have found that the fewer relying on general purpose principles has worked better. But it might be definitional. It might be in my own head that I am looking for general principles. You have to remember, so all the discussion of different kinds of people, well, I would like go beyond people and look at all the animals as well. So it turns out there are principles by which all the animals work. Dogs and rats and people and chimpanzees. We recently found temporal difference learning that operates in people and in monkeys and in rats. The same learning algorithm seems to apply in all these animals, and even applies in insects. In the brains of honeybees, they have found temporal difference learning in their neurons. What appears to be, it's an observation, but the principles and the rules seems to be the same. When we talk about something like search, whether it's heuristic search or or Monte Carlo tree search, it's a very general principle. I mean, it's just, look at all the possibilities and pick the best. So what's a third general principle? I think a third general principle is gradient descent. Deep learning is all about applying gradient descent on a massive scale. So we've all known about gradient descent and stochastic approximation. I don't think the answer is to do those things in a really special, fancy way. The idea is to do them well, do them on a massive scale. That's what we've learned with deep learning. And it's just revolutionized these fields. So it's kind of happened over and over again. Now, I have a little bit of advantage because I'm talking about a science of mind, which is not specific to biology and not specific to machines. So I'm really looking for general principles of mind. I actually think those are three that are real. Search and stochastic gradient descent and temporal difference learning seems to be general principles. Are there other comments? So yeah?
Going back to my earlier question, I think it would really help to have more concrete definitions of human level experience. So there is one, there's the Robocop goal, or playing soccer like Messi Barrier, very good thing.
Yeah, I think it doesn't really matter because we will reach that some level and then we will keep going. There's uncertainties in definitions, but there's also uncertainty is when the computer power will be available. You really think that's?
You'll be speaking about the power now, right? But when you say there will be human, there will be AI, right? What do you have?
I'll repeat what I said before. I'm talking about when we will understand the principles, which will make this possible. So if we can create sensory motor abilities and intellectual abilities, I'm just not concerned with this part at all. Okay. Undoubtedly, it will be, we will never be equal. There will always be differences. Obviously, I did not persuade you that there's this ability that will clearly be happening. Yeah. I don't know. To me, it's. I would say yours would be the extreme view. We tend to talk about, IQs or other ways, general ways of measuring intelligence, and those are definitely too extreme the other way because there are many things to measure. The ability to achieve goals, whatever those, we have to define the things. I tried to do that what intelligence is, it's the computational part of the ability to achieve goals. So it's not that a machine can lift more weight than we do, but can solve intellectual problems, which I think takes things like search and managing sensory motor streams, and I think those are essentially single packages, a few skills. Any other comments? Okay, so in the rest of the time, I want to go a little bit, just one step deeper, still talk about ambition, and just sort of test this last thing that I said, which is that reinforcement learning is consistent with this trend. Is that really true? What does reinforcement learning? It means you learn a value function and a policy. It could be a complicated policy, a complicated value function, lets you solve some task. But this doesn't scale. This doesn't really scale because we just learn one thing, what to do. And I don't think that is a complicated thing. Once you've learned a policy for your game, or this is not this is not a, it's sort of like a narrow thing to learn. Whereas life and the things that people learn are much more complicated. And it's more like learning a model of the world. So like this quote is from the workshop introduction, that reinforcement learning is about new ways of modeling system dynamics. And I think that we really need to do something that's closer to that, or closer to knowledge of the world. So this is broad. To model the system dynamics means you have to predict all the different things that might happen. You have to predict where the ball will be. You have to predict where your feet will be, where the opponents, how they change, what information you will have available if you look in a different direction. So there's this little phrase, modeling system dynamics. It's a big deal. And it's more than classical reinforcement learning, just learn the one thing. We have to interpret RL in this broader way. And then maybe we can have something that's large enough to learn that it could be consistent with the megatrend. So we want to move in this direction. We want to talk more generally about modeling system dynamics, and I want to think of that very generally as knowledge of the world. Okay, so if we look in reinforcement learning theory, there's an obvious way to do this, at least to me, and that's to use this technology called options. An option is a large action, temporally abstract action. Formally, it's a policy with a termination condition. So you would have an option for something like, well, trying to get past the soccer opponent on the right, or trying to set up and execute a kick, a shot on goal. Or you might have an option for walking to work, or an option for even taking a job at a new location. Okay, so an option is a temporally extended macro action. It's like an action, but it's big. An action is going to be defined as the individual motor signals sent to your muscles at a moment in time. Okay, so we have to abstract beyond that in time. Formally, it's going to be a policy, a way of picking actions together with a way of ending that policy. So walking to work would be how you walk. It ends when you got to work. So it's just going to be these two functions. Pi is what we normally call our policy. Gamma is what we normally refer to as discounting, which we will now generalize to be a way of terminating. So my grand ambition is to fully integrate, this is not as grand of an ambition, but it's to integrate the idea of options with the architecture of our agent into a lifelong learning architecture. And you have to ask, why is this grand? And it's grand really because it would require rethinking a lot of things. System modeling, of course, we want to generalize that as far as world knowledge. All that system modeling will be used by a planning system, which would be like reasoning. And then we will have to continue lifelong learning about the world, forming models gradually. This will require a special kind of learning called off-policy learning. And this will also, I think, require us to rethink what we mean by perception as prediction. So let me talk for a while about prediction. Actually, no, I want to, sort of my idea today is to tell you how I think about all these ideas and, try to use them in sentences. So options you can think simply of as a macro option, a thing to do, and a way to decide that you're done doing it. Okay? So now the model of an option, which we're just going to call an option model. Options just sound like action. Option, big action. An option model predicts for each stage in which you might start the option, you predict where you're going to end. What will the state be when you're done, and how much reward will you receive along the way between starting and finishing? So that's the model of an option or an option model. And these are designed so that they're interchangeable with our conventional models like transition probabilities and immediate rewards of a Markov decision process. So if we can so option models are of this form, and they can be used in this way, so we'll be able to use them for planning, dynamic programming style planning, we'll be able to use them in temporal difference learning methods. And now the newer thing, general value functions, GVFs, general value functions. It's a stereotyped, it's a class of prediction. It's a prediction technology. And we're going to make predictions about the options. In a sense, a model of an option is a prediction about the option, right? We predict what will the state be at the end. We predict what will the reward be along the way. But there are other things you could predict about options. They're just a way of behaving and a way of terminating, so there'd be many things to predict. And so general value functions are just a prediction. Now they include conventional value functions as a special case. Conventional value function, of course, is a prediction of the total cumulative discounted reward if you follow a policy. And so that's a special case where the termination is exponential and a little bit on each time step. That's the exponential termination. And then a bunch of general value functions together can form an option model. If you make a GVF to predict the reward that will be received along the way, that would be just one GVF. And then for all these states you might reach, well, you might reach many states. If you try to predict all the states that you might reach, you try to predict arriving in them at the end of the option, put those two things together and you can form an option model. So I'm sure these are the main objects. Options, the ways of behaving, their models, and this general technology for prediction, GVFs, from which we can form the option models and value functions. Okay? Okay, good. And so, yeah, of course, these are the unit. The atom is the GVF from which you can make the models. So my unit of prediction, my unit of knowledge. So here's sort of an informal example. This little robot wants to connect up to this thing, which might be a battery charger. So he'll ask, if I execute my procedure for trying to connect, will it work? Okay? Would try to dock succeed? And the cool thing is that he can make a prediction and then he can try it and see if it does work. So that the semantics of his knowledge is grounded in the data, and he can verify it for himself. Where an old-fashioned approach would say, oh, here's a picture of the thing on the wall, and then a person would say it's a charger or not, and you'd be right or wrong if you agreed with the person. So that is the way we've usually thought about pattern recognition and perception. Much better, though, to think about it in terms of procedures and how they might be successful or not, what their outcomes would be. Because then you can verify it automatically, and if you can get humans out of the loop, then you can take advantage of the computational megatrend, and you can scale with computation, and you can just have the robot interact with the world and get its own data and learn and learn and learn. Okay, so the foundation of this is prediction, and particularly prediction in terms of general value functions. And it's a foundation really for all human knowledge, all scientific knowledge anyway. You can express it as predictions, contingent on a policy. All scientific knowledge can be expressed as predictions. The notion of an experiment maps right onto the notion of an option. What is an experiment? Well, it's some things you do, and then along the way or at the end, you measure something. So it's a thing you do that ends, like an option, and the conclusion of it is the model. When you predict what will be the outcome of the experiment, you're forming a prediction about the option. And so we're thinking that prediction is also the foundation of mind. And one way it's very appealing as a way to gradually figure out how the way of the world works is it works at the beginning and it works at the end. So at the beginning, when you don't know anything about the world, you can do simple things and learn simple relationships. I don't know, if you apply a force if you don't talk about forces at the beginning, you just talk about muscle twitches. If you twitch this muscle that we would call your elbow, well then certain sensors will change in a certain way. You close your hand and you'll feel the pressure on your palm of your own fingers. So even from the very beginning, there'll be things that'll be easy to predict, and yet in the long run, things that are hard to predict will also be, or very abstract concepts will also be available to you as predictions. When you try to do ultimately scientific experiments, again, for very high-level abstract views, the notion of prediction is helpful. So I think it's our atom to understand knowledge. This, of course, has deep roots in philosophy and psychology. It's basically related to empiricism and logical positivism. But I like empiricism, but I'm not going to assume that you start with no knowledge. Of course, that's crazy. The other thing that's different from the philosophical ideas is that we're going to talk about, what the agent can actually measure, rather than what, some universal observer might measure. So let's try to be a bit more grounded. This is my objective for today, is just to get us through to the end of general value functions and give you a feeling that they're concrete. So now we're going to measure, we're going to let time will go, say, every 10 milliseconds. We get a new sensory vector and a new motor vector. That's our data. When I say prediction, it just means some statement that you make at time t about what will happen for times greater than t. And we will assume repeated prediction. So at every t, you're going to make the prediction again. Okay? Special case is at time t, you say something about t plus 1. So about what happens at t plus 1. So that's a one-step prediction. Unfortunately, so much of engineering and machine learning is about one-step predictions, which is a very boring special case. It doesn't get you anywhere near knowledge. It doesn't even make you a very good system model of a physical system. So if you have something where you're at each time t, you're saying about many later time steps, that's going to be a multi-step prediction. And multi-step prediction is the interesting case. So how can we prediction is my key idea. I have to break it up, look at it carefully. So I'm going to break it up first into what I call the question part and the answer part. So if you think about, you make a prediction like how long the Modi government will be in power or something like that. Or any of these, they have both a semantics and an answer. So the semantics is the question. Something like how much rain will fall in the next 24 hours, and the answer is just some number. Will I win this chess game? Some probability. So here's the one for value functions. What will be the discounted sum of future rewards from here forward? The answer again will be a number. So the question describes the procedure. Describes the option, basically. The option describes the option, and the thing that you're measuring. Okay? And the answer is just whatever the answer is. It's going to be a number. And that number will be the expected value of the number that will be calculated by the procedure. Okay, so answers are kind of familiar. If you think about neural networks, they are answer processes. A deep neural network will take in a state and give you maybe a prediction or a label. It's answering some question, but the question is normally not familiar, not so present. And well, that's what I need. I guess I have a whole glass right here waiting. So when we make a deep learning system that will recognize cats or whatever we ask it to do, the part about what a cat is not in the system. It's just, it has no way of knowing if its a prediction, if its labels of a cat is correct or not, except by asking a person. So this is what we have to avoid, relying on people to give us our labels. Okay, so let's talk about some cases. Talk about predicting some signal. So this is a signal. We might want to predict what its value will be in n steps. The word prediction is so small and familiar that we have to really think to realize that it's a complicated thing, because there are many, predicting a signal. Even just, I'm only going to predict one signal. There's going to be a designated signal, and every prediction will predict the value of that signal. But just to say predict the value of that signal, that's enormously underdetermined, because that signal will have a value a different value at each future time point. When I say I'm predicting that signal, that's not enough. I've got to say specifically what do I mean. So maybe I want to predict what it will be in exactly n time steps. That would be a question you could ask about the world. But it's neither an easy question to answer nor a particularly useful question to know the answer to. A slightly more useful thing is to say, well, what will it be roughly n time steps from now? Be easier to answer than what will be exactly, t plus 100, t plus 1,000. Right? Or you're walking to work, you sort of have to predict, I will be at work when I'm done, but there's no particular time, there's no instant, no tenth of a second where you're at work. So we need to fuzz that out or do an exponential thing. This is what we do in value functions. We say, well, was it going to happen in this region? Or we might propose an arbitrary mixture. So I'm just, we're familiar with this from reinforcement learning, where we make a value function. The value function is the prediction of the reward. We say, the value function predicts how much reward I'm going to get. But we know that's just a loose way of talking. Really, it means explicitly a weighting on the future reward. We weight it by how delayed it is with the discounting factor. We also only predict the expectation of the sum of the reward, right? So it could be a small reward that's certain, or it could be a large reward that has a small chance of occurring. We always reduce. We're making a prediction about this whole string of numbers into the future, and we reduce it to one number. So that's an amazing loss of information. It's a small statement. First, another way in which it's small is we're only talking about one signal. We're not talking about, say, the correlation between two signals. So I want you to sort of see the difficulty of the problem and the trade-offs that have to be made to make a general value function, to make a general language that is meant to capture all forms of knowledge. Okay, so what is this form? Maybe I'm actually going to give you the equations pretty soon. It's inspired by optimal control and the value functions. It's particularly, we're choosing it. We're going to choose it so that we can learn it in an efficient way and in such a way that we can then use it in planning. Okay, so let's look at the GVF. And as I said, for every prediction, there's a question part and an answer part. So the question part, it's very much like a value function. That's why we call it a generalized value function, or general value function. So we're going to take a policy, right? It's going to be a policy and a termination condition. So a policy is a map from the action space across the state space into the probability of taking that action in that state. We have to specify the signal that we're going to add up. And this is like a reward, but the whole point is that it's not just a reward. It could be any signal. It could be some light sensor. It could be some abstract signal that's computed inside your deep network. But this is just going to be a single real number. I'll often just call it the signal, but I may call it the cumuland because it's the thing that we're adding up. And then we need the termination condition, which we usually think about as discounting, but we're going to generalize it as a map from the state space to 0, 1. So it's sort of like the probability of terminating in the state that you've arrived in. This is the state space, right? And so then the value, the true value, is the expected sum of the cumuland, just like in a value function, up until termination, if the policy is followed. So we're going to sum expectation of the sum of the rewards, but each reward is, now in conventional reinforcement learning, in conventional value function, this term would just be gamma to the power of t. Gamma to the t would be here. So that generalizes to the product of all the previous gammas in the states that they're in. So we want to know this generalized notion of return. We want to know its expectation, given that we start in the state, and then we're following the policy. policy pi. So this is the generalized value function, but this is the question part. This is what you're trying to compute, the semantics of it. So we don't normally have this even in reinforcement learning. I mean, there's no part of the machine for which this is written down because it's implicit. We assume that you're always, the reward is the reward, so you don't have to say what the reward is. It doesn't change. But now the reward will be different for different. We'll have many value functions, many GVFs, and the whole collection of them will be your body of knowledge. Each one will have a different cumuland, they'll have a different policy, and a different termination. And so this will be quite different for each one. Questions on that? Excuse me? It is just what it is. So there is a specified policy, and there's specified termination function, and so that corresponds to n option. But for the same option, you might have multiple cumulands. Okay, so you'd have a GVF for each one. Sometimes I say v sub I for the ith value function. There'll be many value functions with different cumulands, different policies, different gammas, different termination conditions. Yeah. So then the answer part. Well, the answer part, of course, is going to be a network. It could be a linear inner product. So you have to specify some way your parameterization. You have to identify a set of features of the state, and some kind of, this could be a deep network, or it could just be a linear function approximator. Somewhere mapping from states and a parameter vector, theta, we're going to call it theta in a minute, to the estimated value. And you're going to need a bootstrapping function, which will, normally lambda is a constant scalar. Now we're going to allow it to be a mapping from state to that scalar between 0 and 1. And I'm also going to add an interest function, which allows us to say I care about certain states more than other states. So how interested am I in getting that state accurate? Okay, so, and of course we have to have a source of data. Our answer, the answer that we get will be influenced by the data we get. So that's part of, so these 4 things, right? Before I had 3 things. The question, this is back at the question is determined by these 3 things. Pi, gamma, and the cumulant. But the answer is going to be determined by these 4 things. The parameterization, the lambda function, which states you're interested in, and your source of data. The source of data is another policy. This is parallel to pi. But this is pi, mu is the policy that you're actually going to follow and actually going to generate the data. You want the value function for pi, the target policy, but you're actually going to get data according to mu. Okay, and then we want to find theta that makes us do well according to this measure. This is the thing we'll try to find the parameter for which are approximate. So we're looking at all states. How likely am I to be in that state under my behavior policy? How interested am I in getting that state correct? And then we look at the squared error in that state. So this is the estimate. V of S theta, V hat of S theta is in terms of projected Bellman error. This is the lambda-based Bellman operator that we saw we've been seeing for many years. This is basically the Bellman operator. We apply that to the value function, and then we project back into the space. We form an error. We try to minimize that. So that's the answer part. Here's an example from a robot. This robot is just going around and around the pen and has a bunch of sensors. There's a light here just that shines on it, and it has many photoreceptors on it. And one of them is shown here in blue, in green. So this is 3 trips around the pen. And as it passes the light here, one of the photosensors goes way high and actually saturates up here. Okay? So the green is the actual data. And what's shown here in this dotted line is the target This is like the return. This is the ideal prediction. This is that sum of the future values of the cumulant. You can't actually know this, right? You can only know this after the fact. But we've written it in here, and then so that we can then see how well our predictions, which do use the data, they follow the same shape. Here they are going up, reaching maximum, just at the time where you first saturate, and then they fall during the event. So it shows system learning to make these kind of predictions. Call them 8-second predictions because the discount rate is just a constant in this example, and it corresponds roughly to 8 seconds. Here's another example where we have a non-trivial termination condition. Basically, it's a number that corresponds to an 8-second timescale, a constant number. But if we do ever saturate this sensor, then we terminate absolutely. So that's our sort of our envelope of prediction. And then what are we predicting? We're predicting power consumption by the robot's motors. Okay, so this green line is the actual power consumption. And predicting it this way, we basically predict the sum of the power consumption weighted by an 8-second time scale, this exponential envelope. But if we do ever saturate, then that's the end. So we don't predict things past the time of saturation. This gray is the time of saturation. And so here it's predicting, again, the dotted line is what it should ideally be predicting, and the red here is what the prediction actually is. But the semantics of the GVF is suggested by the dotted line, and that prediction should go up prior to saturation. Once saturation happens, then the prediction is very small because very little can happen before things end again, and then it jumps back up when we start the next cycle. Here's one where we're predicting the imminence of an event regardless of its duration. I want to say, and what are we predicting here? We're just predicting the event of being close to the wall, which is a computed quantity. Both n is the prediction, n is the thing being predicted. So it's 1 when we get there, but then it ends the prediction. So we can predict a substantial variety of things. Okay, now I want to finish up, leave a little time for questions. So let's just notice that first, these are all multi-step predictions. It's all critical to being able to express complicated things. And you can ask, do we need to use multi-step predictions? Can't we just use one-step predictions and then iterate them? Or can't we just think of multi-step predictions as one big step and then use our supervised learning one-step methods? And the answer in short is that we can't. We can't learn one-step things and iterate them because although in theory it works all right, in practice, just because your one-step predictions can never be exactly correct. If they were exactly correct, you'd be all done. You would just iterate them. It would be extremely computationally expensive, but you would have enough information. But in practice, there's a branching factor in the world, either because the world is stochastic or because you have choices, and that makes it computationally infeasible to make long-term predictions in this way. And just if not more important, if there's any error in your one-step predictions, that error will propagate and expand exponentially with how far ahead you're looking. And then, so your multi-step predictions will all be poor if you try to build them in this way. And you could try to, wait and look at the later data and form a pair out of that and use supervised learning. But you will have significant costs, beginning just with the cost that you have to remember all your predictions. It's like you're trying to predict who will be the next president. You'd have to remember every prediction you made on every day on the 4 years leading up to the election and the reason for which you made each prediction. You'd have to remember all that, and then you'd have to, once you finally figured out who was president, you'd have to go back and change all those things. It's very inconvenient computationally, and we shouldn't ignore these hints from the world. Let's also notice that all the interesting concepts, perceptual concepts, are of this multi-step form. So more abstract and more cognitive things. Can you hit the pitch? Can you kiss the girl? Can you sit on the object? Can you interact with this device to get your email? These are all multi-step predictions, and they're a much better way of structuring our way of understanding the world. The algorithmic issues, we need things like eligibility traces, temporal difference learning, and you can apply all the standard temporal difference learning methods to learn general value functions. Really, we would need to use off-policy learning. I'd like to close with some robot examples. So the robot examples is going to use this architecture, where we take in sensory motor data, expand that up into a high-dimensional feature space, and then we're just going to use a linear map for each prediction. So here we show some number of predictions or prediction daemons, GVFs, daemons, same things. Each daemon is learning an estimate of the general value function with a different question. Okay, and in some cases actually we then feed the predictions back into our expansive recoding to get a recurrent system. With that architecture, then we can have our robot move around and gather data and make predictions. So, I don't want to take too much time, but this robot has sensors all around it that can see into the distance. So as it passes this wall, for example, that sensor number 2 goes high, which is the red. So that being empty means it's blocked, and if it's open, then we see this sensor goes up. It goes up right there. Okay, and in the first row is the prediction of that. So the prediction is low at blue, but as it approaches the wall, it will go up to be green, and then the sensor will come on. As we go backwards, it turns blue, and then the bit turns off. So you can see it's making prediction about that sensor, but it's also predicting all the other 9 sensors. So we have 10 GVFs all being learned in parallel. So this is the way we're looking at the problem. Here we have now, I don't know, a few hundred predictions, and there are still about these 10 sensors, but now we're predicting, will the sensor, not will it just be present or absent, but what value will it take on? Actually, we break the value space into 16 different values. We predict each value independently, and we're also predicting for different options, for different ways of behaving. What if I go forward? What if I turn right? What if I move backwards? So for each option, we make a different prediction about the probability of arriving in each one of the intervals of the sensor. So it's very easy to get large numbers of predictions in this way. This is a different robot rotating here, and it's just trying to predict some of its CLIS sensor inputs. I think I'll skip over this one. This is the same robot. Now he's scaled up to a few thousand predictions with thousands of features, but it's the same architecture. So these, the sensory signals, original sensory signals, are shown up here, varying as the robot's moving around. And then the expansive binary state space is here, and those all signals are changing as it moves around. And then the 6,000 predictions are shown here in the same code as before, where blue is low and green is high. So it's easy to scale this and have it run. Well, it's never easy to make. This is actually stresses the ability of a modern laptop to learn 6,000 predictions with a few thousand features. But it wouldn't be possible at all with classical prediction methods that don't use temporal difference learning. Okay. On another day, I'm going to tell you all about off-policy learning. That's one reason why this is challenging. But off-policy learning is really learning about one thing while doing something else. Here's a case where we just had the robot move around randomly, but it was learning all while it was moving randomly, and it was learning how to run and maximize its light input, which here the light is here, and it learned how to run quickly there. So Horde is the name we use for this highly parallel architecture. And we could just ask, maybe this is where we should stop. Is this a good way good way of modeling system dynamics? This is all in the form of questions, and they remain questions, but the key to this slide is that basically I want to say that the answer might be yes. So it might be complete, and it might be sufficient to correspond to all necessary world knowledge. This is really an open question. But yes, they are suitable. They could be suitable for planning. Remember, this is the ambition. All these things have not been done. Certainly, they can be made in a plug-compatible forms for the planning methods and make an option model. And even learning efficiently is a challenge if they're off policy. Okay, so basically I'm suggesting that just as value functions are one of our keys to reinforcement learning, maybe we can use them for world knowledge, and they're crafted for efficient learning. Okay. I want to close with one more robot example. This is going to learn as we're watching it, so it starts out not knowing anything, and it predicts bumping into the wall. This is a standard create robot. You can see it a little bit better here. There's a bumper in the front, and there's a camera. Okay, and all the processing is on board on a Raspberry Pi. So it's just moving and trying to predict whether it bumps into the wall. And when the prediction gets high enough, then instead of continuing forward, it turns. You saw it right there. And the walls are all slightly different colors, and it has to be learned about each one. But after a while, when the predictions get reliable, it will not actually bump, but will turn before it bumps. Okay, so this is both learning a prediction and using the prediction to avoid bumping. Okay, so some conclusions. General value functions are much more expressive language than ordinary value functions, and more powerful than they might at first appear. I'm sure that, I hope that's just a question in your mind, that there are some things that maybe you might have thought we could do. You could just, by changing the 7 things, the three things determining the question, and the 4 things that determine the answer, to capture a wide variety of cases. The predictive aspect provides the semantics, the questions provide the semantics, and they let us do both intermediate and advanced kind of prediction. And predictions are involved in so much mental activity that we might consider them to be the coin of the mental realm. So today I've tried to tell you a little bit about the ambition that I and others have about reinforcement learning and AI, and we really want to gather more and more value functions, more and more predictive knowledge about the world, and ultimately this is a strategy for scaling up and reaching towards human-level intelligence. There are many, many sub-challenges involved in the learning processes and the representational processes and the planning processes, and but we're starting with the elementary tools of learning and planning. And thank you all for your attention. So that clock is fast, but we are just past 10:30. So I'm not sure how you want to handle it. The I function is the interest function. That's new, but I think it's inevitable that we express to what extent we want to make the predictions accurate for different states. So it becomes important once you're using function approximation It's kind of underappreciated that once you use function approximation, you have to trade off your degree of approximation in different places. So for example, one common way to do robot experiments is you want to get the start state at maximum value. You don't really care about the other states. You have to capture that somehow.
Do you have algorithms for the error functions that you described?
We have a new algorithm where we take into account the interest, the I. We don't have algorithms for setting it. But we have algorithms that use a user-specified degree of interest in different states. Yeah, and I'll be talking about